So this chapter we are focusing on the electron. Like I said, the electron is the main character a lot of times in chemistry. So we want to know all about how they are understood to be part of the atom. So in this section, first section, we're going to be looking at the atomic model, but first we have to talk a little bit about light to be able to understand it. So a little math at the beginning here, doing some relationships between speed, frequency, and wavelength. We're going to talk about how light is both a wave and a particle, and look at the photoelectric effect, which is actually what Einstein won a Nobel Peace Prize for. And then we'll finally develop the Bohr model, which is a step further than we were with Rutherford's model. So first we have to define light. Electromagnetic radiation sounds like a fancy word, but it just means light. And light is any energy that travels through space. It exhibits wave-like behavior. And there's all sorts of forms of light, not just the light we can see. There is other types of light that we'll talk about here in a second. But all these forms of light are on the electromagnetic spectrum, which looks like this. So notice on the electromagnetic spectrum, we have some energy, some lower energy, lower frequency waves on the left hand, and then some higher frequency waves on the right. With visible light, you look at these two blue lines here, very tiny spectrum that we can see on the whole gamut of light rays. Notice some of the lower frequency waves, like your radio waves, are very long. They cover long distances. That's why we can hear radio waves. We can get broadcasts from television from far away. Those radio waves are always traveling through the air. They're through space. They're all around us. Even our cell phone towers have the radio waves, a little higher energy radio waves. By the way, the lower energy, if you're familiar, the AM radio versus the FM radio, you might look on your dial and see that it's in megahertz for FM. That actually is related to the frequency that we're talking about here. AM radio waves are longer. They travel further distances, but FM, a little bit better quality. So then as we go up the chart here, we've got microwaves, which are not the shortest, but they are found in microwaves. They are the energy that you can use to cook your food. They give your food in the microwave enough energy to vibrate the water molecules. It's actually what cooks your food is the constant vibration of those water molecules. Infrared is essentially heat. Infra means below, so infrared is below the red. And if you ever look at a heat lamp, there you see some red light mixed in because it's very close to red on the visible light spectrum. If you see like an incubator with chicks or anything like that, you might have seen infrared light. Visible light we're familiar with. It's Roy G. Biv, the colors of the rainbow. Everything we can see is a bit visible light, essentially. I know bees, I'm pretty sure, can see ultraviolet rays, which are a little bit higher energy. They're above violet, so I don't know. If you've ever seen something that's using UV light rays to dry something, the only thing I can think of is like when my wife gets her nails done, she puts her fingers under like a little purple thing that's UV rays to dry them faster. And you see a little bit of that leftover violet light as you're doing that. Or like maybe tanning salons, tanning beds, you see that a little bit. Notice though, the light starts to get a little bit dangerous as we hit this. They tell you not to tan. Use SPF sunscreen. because ultraviolet rays can do damage to your skin, but it's not like we're terrified to go outside because they're that bad. But they are a little dangerous. They can be a little dangerous. Up the chart, we have X-rays, which are even more concerning, right? Because if you're getting an X-ray at the dentist, the assistant always runs out of the room because they don't want exposure to those X-rays all day. They also put you in like a lead vest to trap some of the X-rays. Because X-rays are strong, they can do damage, they can go through skin, but they don't go through bones, which is why we're able to see pictures of inside your body when we use X-ray technology. Finally, gamma rays are the most powerful, the highest frequency waves. We see some nuclear reactions producing those. And that's why with nuclear reactors, you see thick concrete walls to try to trap those rays, that radiation. When you see like the big danger radioactive, you might be seeing rays in that range. So one thing I want to talk about with waves is the properties. So these light waves, they all have a wavelength and a frequency. And I'm going to do this. I actually prefer to refer to frequency as F personally. Our textbook goes with V, but with physics, I don't want you to get that confused with velocity. So in my calculations, I'm going to write F. But I want to talk about wavelength and frequency. Wavelength is the distance between corresponding points. Frequency is how many waves pass a point in a given specific amount of time. So I have a little demo. And there goes my PowerPoint. But I have a little demo here. It's already going. We have a wave being generated here. If I pause it, notice the wavelength is my distance between two corresponding points. So I might use two peaks or two crests of the wave. I could use two valleys, which are called troughs. If I measure the distance between those, that's one wavelength. So notice a wavelength has to complete one full iteration of the wave. Now frequency, on the other hand, notice every time it goes out the window, that's how fast the wave is going. I can increase the frequency, and now it's going like a lot faster. We're counting how many times per second the wave is moving past a point. So what happens to my wavelength as I increase the frequency? Yeah, the closer together, the wavelength becomes a lot shorter. So as I increase the frequency, wavelength decreases. As I decrease the frequency, wavelength increases. They have what's called an inverse relationship. So back to my notes here. So we have an equation that shows that. If I multiply them together of light, I actually get the speed of light. Because with a wave, if I measure the length, that's a length measurement in meters. If I measure the frequency, it's like how often does something happen over time. So it's like per time or per seconds. We have a fancy name for that unit. It's called the hertz, like the car company. And we abbreviate that HZ. That's a per second. So if I multiply meters by per second, I get speed, which is meters per second. And that value of C is the speed of light. You might have seen it in E equals mc squared. But it's 3.00 times 10 to the 8th meters per second. In your calculator, nice and easy, just type 3E8. in this equation, if you like triangles, we'll make another triangle. Some people don't like the triangle. But we're going to put C on the top, wavelength. And like I said, I prefer C equals wavelength times F. C equals wavelength times frequency. If you like the V, or the new Greek letter, which, by the way, the Greek letter, that upside down Y looking thing for wavelength, that is called lambda. And they, instead of W, they just use an upside down Y, because why not? You recognize it from Half-Life. So these math equations, these math problems we do with this, the step is the same. It's nice because the step is the same for both. We always know what C is. We always know C is 3 times 10 to the 8th. So we're either going to be dividing by wavelength or dividing by frequency. Whichever one you want to get, you just divide by the other one. So we have a little practice worksheet up on Canvas. It's homework 4A. We'll go over that together. There's a couple problems I will do. A couple problems I'll have you do. So the first question there, calculate the wavelength of yellow light emitted by a sodium lamp. So I'll draw my little triangle just for reference. C, wavelength, frequency. So they're asking me to find the wavelength. If I cover up wavelength, I'm going to divide C by F. So wavelength is C over F, which is 3 times 10 to the 8th meters per second over 5.10 times 10 to the 14th hertz. Just want to remind you that a hertz is the same thing as a second to the negative first, which means per second. So my units check out because I have a per second divided by a per second, and I'm left with meters. So in my calculator, I'm just going to take 3E8 divided by 5.10 E14 gives me 5.88 times 10 to the negative 7th. Now, because I'm familiar with it, I know yellow light is in the range of a few hundred nanometers. This is times 10 to the negative 7th. Nanometers is times 10 to the negative 9th. So 588 times 10 to the negative 9th would be an appropriate value for yellow light. Any questions on that one? We see how to do it. Now you might see this number looks a little familiar in question 2. They got 5.89 times 10 to the negative 7th. Really similar, but except this time we're finding frequency. So I'm going to take C divided by wavelength, and then I'm going to take 3 times 10 to the 8th divided by 5.89 times 10 to the negative 7th. Meters will cancel out. So I get 3E8 divided by 5.89 E negative 7. And lo and behold, it gives me 5.10 times 10 to the 14th. Which is exactly what they were asking us in problem 1. It's going to be in per seconds. I know that per seconds are hertz. My meters cancel out. So be good with those first 2 problems. So what I would like for the rest of the time here you guys want to try 3 and 4, just to make sure we're good, and then 5 through 10 are going to be the homework.